Hey everyone, welcome back to my channel. Today I want to explain something unusual but incredibly powerful category theory for AI agents in a simple and intuitive way. AI agents promise to plan, reason, search the web, call tools, and automate work like a digital co-pilot. But what we actually get? Hallucinations, broken tool chains, unpredictable behavior, and system that collapse as soon as it gets complex. And it is not the LLM's fault. When you combine reasoning, memory, tools, API scratchpad, planning, and state, you don't get an agent. You get a network of moving parts with no unifying structure. It becomes brittle, impossible to debug, and dangerously unpredictable. The real problem is orchestration. We are building skyscrapers, but without any blueprint. What we need is a mathematical design of the agents that are modular, composable, and safe. That blueprint comes from a surprising place of mathematics, category theory. A field of pure math that turns out to be the design language for reliably AI agent systems. Don't panic. This is not about calculus or abstract equation. Category theory is simply the math of structure, equations, and relationships. And at its heart, a category has only three places. It basically consists of three things. One, objects, morphism, and third one, composition. You can see here. Now, what are the objects? Well, objects are the things in AI. For example, if you think about the category of sets, what you can see? Suppose A and B are sets. This A and B, they are objects. And F is a mapping from A to B. That map F is a morphism. If you think about the vector spaces, the vectors are the objects. And the linear transformation T from A to B, this is the transformation. Now the question is, for AI agents, what are the objects? What do you think? Can you tell me what are the objects for AI agents? Correct. For AI agents, the objects are the states. And what about the actions? What about the morphisms for AI agents? Actions. Yes. So what we see that actions takes one state to another state. That action is the morphism. And composition means the rule for chaining the arrows together or chaining the morphisms together. I will come back to it. First, let me explain this, and later I will explain about what is composition in detail. Now, category theory does not ask you what is inside A. It is not concerned about that what is inside A, but it is concerned about the connections from A to B. How does A moves to B and B move to C? Can we compose them? If A goes to B and B goes to C, then basically you can get A goes to C. This simple idea is the foundation for turning chaotic agent code into predictable, modular, and structured workflow. Now, let's make this real with an AI agent example. So when you ask an AI agent, what is the weather in London right now? The agent does not magically knows the answer. It follows some certain steps. It goes through a series of steps. Number 1, user query. Number 2, thought state. Number 3, API request. Number 4, API response. Final answer. So basically, these all are the states. You can think them just like states. So you can see that these are the objects of the category, right? We know that these are states, and you can think them as the just a minute. Yeah, you can think them as the objects of the category. They are the container of information. Now the question is, how do we move from one container to another container? Through morphisms, actions. Parse transforms the user query into a thought state. So you can think parse as an action. Second one, you can see plan. Plan turns the thought state into a structured request. Third action, call API. It basically turns into an API response. Format converts the response into a human answer. So now you can see that how we can think actions as a morphism in category. Now, next, composition. I told you initially that I will explain it later. Now, so basically, what is the mathematical term of composition? Suppose f is a function that goes from a to b, and g is a function that goes from b to c. Then f composition g, it goes from a to c. So this is the main idea, mathematical idea of composition. Now the question is, how can we use them in AI agents? Well, here you can see, I mean, in the previous slide, you can see that I have discussed about the actions. Here, what we will do, we'll combine the actions like a composition. Format, composition call API, composition plan, composition parse. This is composition. We are building the entire agent behavior by chaining small, reliable steps. So basically, intuitively, composition means making a big system from a lot of small subsystems. I mean, if you think that way, you can understand this. So this is the engine behind the agent orchestration. And the morphisms are the functions between the sets. That's it. Now, we will see some simple math examples. For example, let's define another set, A and B. Here you can see that B means API call and answer. Now, a function f A to B, what it will do? It will take each element of A and it will connect it with an element of B. Assign it to an element of B. For example, here if query equals to API call. This is literally the same at what an agent does. When it, just a minute, yes. When it gets a query, it produces an API call. When it retrieves memory, it might produce an answer. So you can see how we can connect both of the things. Now, the question is why this makes AI safe and predictable? Now let's talk about why category theory actually matters. Well, the first one is that it gives us a structured workflow design. Right now, many AI agents are held together by duct tape. One Python function calling another, which calls a tool, then another, and the system goes on. It's easy for everything to get messy. Category theory forces us to think in clean stages. State, transformation, next state. That structure becomes the blueprint of an entire agent. It ensures safe transformation. Every step, every morphism has a guaranteed input type and output type. So if a planning step is supposed to produce an API request, but instead it produces an random string, then the system does not break. That's the beauty of category theory. The third one, it helps us build predictable modular agent, because every part of the agent is an either an object or an morphism or arrow. We can replace components, improve them, or even add new ones without rewriting the whole system again and again. It's like Lego blocks. Every piece fits because The rules are consistent. Now the fourth one. It becomes the foundation for advanced agent orchestration language. LLM agents are getting more and more complex. Memory, modules, tool chains, planners, retrievers. To manage all these, we need a formal language to describe how these components interact. Category theory gives us that language. It is the mathematical building block for building reliable, safe, scalable, next generation AI frameworks. So, in short, category theory moves from chaotic script to intelligent engineering. Now, what is the impact of this on agent design? Well, the first one is scalability. We can build massive multi step agents that don't collapse under their own complexity. The second one, verifiability. We can mathematically check the logic of an agent's reasoning chain before it runs, and we can verify whether it is right or wrong. The third one, resilience. Agents can recover from failures, retry steps, and keep going instead of breaking with one bad output. This is the future of AI engineering. Instead of hacking together difficult prototypes, we finally get to architect intelligent systems with the same rigor as real software engineering. Category theory is not just abstract maths, it is the missing design language for the next generation AI agents. If you are building AI, you need to understand this blueprint. So that's it for today. If you like the video, then please hit the like button and you can subscribe the channel. Thank you. Thank you so much.